Subtitle. The next subtitle is all about collision. So collision can be stated as you can say like an instant of one moving object or a person in general striking violently against another, like collision of two balls considered to be collision. So commonly in physics there are two types of collision. The first type is elastic collision. The second type is inelastic collision. So there is a difference between this elastic and inelastic collision. We can differentiate the elastic with inelastic collision based on the kinetic energy. In most cases, the momentum is conserved. Elastic collision and inelastic collision between two objects is one which total kinetic energy as well as total momentum of the system is conserved. So in case of elastic, for example, here consider two bolts, they collide with each other. So this is considered to be elastic collision if the energy is not lost in the form of heat or in the form of sound or in the form of deformation. So it's included under elastic collision. So whenever you calculate the momentum as well as the kinetic energy, whenever you say the kinetic energy, the initial kinetic energy and the final kinetic energy will be the same for elastic collision. For example, for these two bolts, this one is in motion, this is at rest, so the kinetic energy of this one at first is 0, but the kinetic energy of this one is not 0, different from 0. Therefore, the kinetic energy of this one, the final of this one is 0, but the initial is not 0. So in such cases, so there is an elastic collision. After striking the second ball, this one has a velocity of 0. So whenever we calculate 1 over 2 mv square, so v value will be 0. So that's why we consider it as an elastic collision. Okay, let's proceed. So the other one inside the elastic collision, there is also consideration of perfectly elastic collision. So this occurs for atomic subparticle. So we can consider this like an atomic subparticle. So if they collide with each other, these atomic subparticles like electrons, like protons, neutrons, they are considered to be the atomic subparticle. So in such collision, this collision is considered to be the perfectly elastic collision. Not only elastic collision, but perfectly elastic collision. Actually, this is not perfectly elastic collision because you can hear sound after the two balls strike with each other. This sound contains energy, so the energy is lost in the form of sound. So it cannot be considered as perfectly elastic collision, but partially we can consider it something like that. But you can imagine that these are the atomic particles, so when one strikes with the other, so it can be considered as the perfectly elastic collision. So an accelerated electrons, when it strikes a certain surface, so there is a collision. So after the collision there will be a diversion of direction. Okay, two particles collide head-on and then leave the collide sides with different velocities. Consider these are the two particles. The first one is m1, the second is m2. This one is moving to the right, this one is moving to the left. This one is moving with the velocity initial v1 initial. This one is moving to the left with the velocity v2 initial. Then they collide with each other. So after the collision, this one is moving to the left and this one is moving to the right. So they are in opposite direction. So the initial, which is m1 v1 initial plus m2 v2 initial, this is the initial. The final is m1 v1 final plus, this is indication of the conservation of momentum. In this case, the conservation of momentum. Therefore, considering the velocity along the horizontal direction, we have half m1 v1 initial square plus half m2 v2 initial square. This is the kinetic energy initial for mass 1 and mass 2. After the collision, this one is moving in this direction and this one in the right direction. they have a kinetic energy of half m1 v2 final square plus half m2 v2 final square. So the initial kinetic energy, the left side, is equal to the final kinetic energy to the right side. Okay, so in elastic collision, we can have v1 initial minus v2 initial is always equal to minus sign of v1 final minus v2 initial minus of the final. So we subtract v2 initial from v1 initial, the initial value of velocity, and the final value of the velocity after subtracting v2 final from v1 final minus the sign will be equal. Let's prove it. So in order to prove this one, we can start from this. That means the kinetic energy initial, which is 1 over 2 m1 v1 initial square plus 1 over 2 m2 v2 initial square is equal to 1 over 2 m1 v2 final plus 1 over 2 m2 v2 final. Okay, by the way, this is v1 final, sorry, make it this v1 final, it's not v2 final. This is not, this is v1 final. Okay, so now both sides multiply by 2, this side by 2, the right side multiply by 2, this side by 2. So when 2 cancel by 2, 2 cancel by 2, 2 cancel by 2, then finally we get m1 v1 initial square plus m2 v2 initial square is equal to m1, this is also not v2, this is v1 this is v1. Okay, so m1 v1 initial square m2 this is m2 v2, sorry, this is 1, this is 2, this is 2, this is 1. Yes, because that is the final value and this is the initial value. This is the initial value for mass 1 and mass 2, and this is the final value for mass 1 for final, mass 2 for final. So for mass 1 we have v1, for mass 2 we have v2. For mass 1 again here in the initial case v1, for mass 2 for initial case it is v2. That's why we make a correction in this. Okay, so finally we get, after these two is cancelled, this will be converted into here. Then after this one, let's collect m1 them together. This m1 v1 final square, take this to the left side and this one to the right side. When you take this to the left side, it becomes v1 m1 v1 initial square minus m1 v1 final square. m1 is common with m1, so right outside, so it becomes v1 initial square minus this is v1 final square. m1 will be written outside. So on this side we have m2 v2 final square, so take this to the right side, it becomes m2 v2 initial. So m2 is common, v2 final square minus v2 initial square. m2 is common, in this case m1 is common. Okay, so after this we know that a square minus b square is always equal to a minus b plus a plus b. A square minus b square is equal to a minus b plus a plus b. Therefore consider this is a square, then this is b square. A square minus b square is a minus b times a plus b. Therefore v1 initial minus v1 final multiplied by v1 initial plus v1 final. For the second case, v2 final minus v2 initial, v2 final plus v2 initial. So after having this one, we know that, we remember that after this we remember that momentum is conserved. The momentum is conserved in such cases. So the momentum m1 v1 initial, m2 v2 initial, m1 v1 final m2 it is conserved, they are equal in such cases. Now when you take m1 in the left side, it becomes m1 v1 initial v1 final. For this case, m1 v1 initial v1 final, m2 v2 final v2 initial. Take this to the right side from the conservation of the momentum. Collect the mass 1 together, mass 2 together, and finally get this. So now compare with the first one. When you compare with this one, we have m1 v1 initial and v1 final. m1 v1 initial v1 final is equal to m2 v2 final v2 initial, m2 v2 final. Therefore these two values are the same. These two values are the same. If these two values are the same, this value is the same with this value, therefore it is possible to conclude that this value is equal to this value, which means v1 initial plus v1 final is equal to v2 final plus v2 initial. These two values are the same. Okay, after this, let's collect the initials together. Here we have v1 initial, here we have v2 initial. So take this to the left side, it becomes minus 2 v2 initial. Take this to the right side, it becomes v1 final minus v2 final. Okay, so when you change this v2 final, v2 initial, when you write v1 final minus v2 initial, we need to write minus outside, because here the right side we have v2 final. Okay, so here v2 final minus v1 final, but if you write v1 final minus v2 initial, you need to write minus outside. Okay, so for elastic collision, we always have the initial subtract v2 initial from v1 final always equal to minus of the subtraction of v2 final from v1 final. Okay, let's proceed. So for an elastic collision, as you can see here in this example, an elastic collision is a one in which the total kinetic energy of the system is not conserved, but the moment of the system is conserved. Therefore, for an elastic collision, two particles we have this momentum, initial momentum, and this final momentum. They are equal, but the kinetic energy, the initial kinetic energy, is not equal to the final kinetic energy. Energy may lost in different forms. Maybe in the deformation, as you can see here, for example, there is a collision between these two cars. There is a collision, so the energy lost in different forms. That's why it cannot be conserved. One of the form of losing energy is the deformation. The sound is by itself, and there are so many things to be considered in the form of heat maybe lost. So this is the best example for inelastic collision. It is not an example of elastic collision. So if it is elastic collision, though you cannot observe any deformation on the car, no deformation on the car, but after the collision one receive, maybe the direction of motion may be different. So this is also another example of inelastic collision. Okay, so perfectly inelastic collision, when two colliding objects stick together, just like these two, they collide each other and then they stick together and they go together. So therefore, after they collide, they go together. So in this case, the final velocity is the same. Final like this one, m1 v1 plus m2 v2. The two masses will be added together because they go together, so they have the same final velocity. So this is an example of perfectly inelastic collision. So again here, this is a perfectly elastic collision. The initial kinetic energy is different from the final kinetic energy due to the loss of energy in different forms. Okay, this is an example. So an archer shoots an arrow. This is an arrow towards a target. This is the target that we have that is sliding towards her. The motion of this target is towards the left direction in the beginning with a speed of 2.5 meters per second on the smooth surface. there is no friction in this one. So 22.5 gram arrow, the arrow has this much mass, which is 22.5 gram arrow, is shot with the speed of the arrow, which is towards the right direction, is 35.0 meters per second. And passes through 300 gram target. This target has a mass of 300 gram, which is stopped by impact. What is then? This arrow passes through this one. It penetrates and passes and goes. So after it passes, this one, the speed of this one is 0. So the speed of the arrow is after passing the target. So the question is, what is the speed of the arrow after passing the target? And this one is stationary. Okay, so we simply apply conservation of linear momentum. So we have to write m1 v1 initial plus m2 v2 initial, m1 v1 final plus m2 v2 final. So m1, we can consider the mass for the m1 would be mass of the arrow possible. So the mass of the arrow is 22.5 gram. This is m1 is mass of the arrow, and the speed of the arrow is 35 meters per second. So m1, the initial is 35 meters per second, plus the mass of the target m2, so 300 gram, and the direction of this motion is towards the left, not towards the right. So that's why we use minus sign, which is 2.5. As you can see here, it's 2.5. The block is moving 2.5 meters per second on a smooth surface, 2.5 meters. So v2 initial is this one. So is equal to mass 1, which is 22.5 gram, v1 final, which is mass of the arrow, plus mass 2, which is 300 gram, which is the arrow, plus times the speed is 0. After this arrow passes through this one, or after it ejects from this, the speed of this one, the speed of this sliding object is 0. That's why we have a result to be 0. So multiply these two together, subtract this value from here, and divide by 22.5 gram, which is this. When you multiply 787.5 minus, when you multiply this one, become minus 750 divided by 22.5. This gram cancelled by gram, and finally we have meter per second, which is 1.67 meter per second, with the speed of the arrow towards the right direction. The speed of the arrow towards the right, or the velocity of the arrow is 1.67 plus 1.67 meter per second. Okay, this is also another example. We have a block of mass m1 and 1.6 kg initially moving towards to the right, and the speed of this 4 meters per second. So this is also an example. And finally they collide with each other, then substitute the values and apply the relation in conservation of energy and the previous formula, like this one, v1 initial, v1 final, v2 initial, v2 final, then substitute it here, then finally get the two results, two unknown speed after the collision. After the collision, the two blocks it's not known, so the first mass 1 is given, mass 2 is already given, initially moving towards the left to find the velocities of two blocks. Then after they collide with each other, it's very simple. Okay, there is also another example that you need to consider. Before the collision, we have m1 and m2. When this one is moving towards the mass 2 is v1, then after the collision, mass 2 is moving in this direction, mass 1 is in this. Between them there is an angle theta. So in such cases, you have to draw a line in between them, a line or horizontal line. Start from here and then measure the angle between the horizontal line and this one, and the horizontal line and this one. Then after that, you have to have a component of v2, final velocity of mass 2, which is x component and y component. You don't need to consider the y component, you need only to consider the x component. So in this case, the momentum m1 v1 plus m2 v2 v2 is 0, so m1 v1 is equal to m2 v2 cos this value. It may be theta minus 60 minus 30, we don't know that value, but this value, after you draw this one from horizontal, you need to measure, and so cos value of that will be the component plus m1 v1, again cos value of the second one. The sum of these two ties already theta value is given, so we can subtract one means the other. First, you need to draw a line between them. Another example that you need to have is when m1 strikes m2 at the distance of this one, the potential energy will change to the kinetic energy. So in this case, it's possible to convert one potential energy and kinetic energy, and it's possible to find the speed of mass 1 at this position. The initial speed of mass 2 is 0, but the initial speed of mass 1 can be found by mg d. D is h is equal to half m v square, so m cancelled by m, 2gh square root is equal to v value 2gh. 2gh means 2g d. D is h value, which is the initial velocity of m1. Then after that, it's possible to find the known value. Okay, so the last part of this chapter is center of mass. Center of mass is the point at which all the mass can be considered to be concentrated. The center of mass of the system is located somewhere on the line joining the particle and closer to the particle having large mass. The center of mass of a pair of particles located on the x-axis shown here, and this one, the center of mass is somewhere around this. So in order to find the center of mass, we have to take mass 1 at the distance of x1 from maybe from the origin or from somewhere. And mass 2 is at distance of x2, so m1 x1 plus m2 x2 divided by m1 plus m2. If you have another mass here, third mass or another mass, two masses, 3, 4, and so on, so you have to write x center of mass is always equal to m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by m1 plus m2 plus m3 plus m4. So it can be written like this: m1 x1 m2 x2 and mn xn. So this is summation of m i's. I maybe start from 1 up to n value, maybe 10 or 20 xi divided by the sum of masses mi. So m capital M is most of the time indicates the total mass. Sum of total mass can also be indicated by the capital M value. So the same thing is for y center of mass. Y center of mass is m1 y1 plus m2 y2 plus m3 y3, and so summation of mi yi over total mass. It can be shown here. Y center of mass is mi yi over m, which is m1 y1 plus m2 y2 m3 y3, and so on. So in general, R center of mass is x center of mass plus y center of mass plus z center of mass. So there is one simple example. It says the system consists of 3 particles, m1, m2, 1 kg, m2, 2 kg. X center of mass is m1, m2, m3 up to, we have 3 masses, therefore m1 you have to add. So m1 is 1 kg, so x1 is 1, m2 is, and x3 is 0 because this is in the y-axis. Third mass is in the y-axis. In the y-axis the x value is 0, so this is 0. So divided by, then finally x center of mass. For y center of mass, m1 y1 is 0, y2 is 0, y3 is already known. So this is 0, 0, and finally y. The center of mass is 0.